This Friday.
So,
If the weather's alright, that is.
we're going to pick up where we left from. Now, you may have noticed beautiful colour printed notes. That's a one-time because the black and white copy was broken. So I'm sorry, that luxury can't continue. Okay, so I guess the first thing I want to talk about is how's those two going? Who's finished? Can I see some hands? Who's struggling? Right, okay. Who doesn't know yet because they haven't started? Okay. Much to the annoyance of those who have finished, I can extend the deadline till Monday midnight. So I'm thinking about that. So if I get enough emails from people who are in desk constraints, I'll do that, but I won't just do it automatically. So if you want the deadline, I want to see enough people ask to have it pushed out to Monday midnight. It can't go further than Monday midnight because, of course, that's when Lab 3 starts. All right, well, today we're going to look more at that data link lab. So we're building that protocol stack that allows us to abstract out the problems of transmitting data over these devices that form a network. Now, where we kind of left off last time is talking about how the data link layer deals with this problem of errors. And we saw in that very first couple of slides last time of how error can be introduced in wired media in particular. But you can also have things like attenuation and stuff. So an error in transmitted data can either be a single bit or it can be a burst. So you might get a single bit, and you saw this interference. You might get a burst of data that interference continues over, say, n bits. So then the question becomes, how do we detect errors? If we only transmit data, so if we're only sending our data and nothing else, we can't detect anything, right? We have no way of telling whether that data is good or bad or whatever. However, what we can do is in those headers we talked about last time, we can send some metadata with the actual data. So that metadata is data about the data. So it's actually not content itself. Metadata is never content. It's data about data. Now, it doesn't mean metadata is not useful. You can, using your cell phone metadata, track where you've been all day. But as far as the actual thing you're trying to send, or telephone calls you're trying to make, the metadata has no actual relationship with that message. So in this case, we can use this data about data, this metadata that we're going to put in the header that we saw, to satisfy some special relationship. So some computation. We can also add redundant data, and we might have to do both of those things in order to be able to detect whether our data is good or not. Now, when we talked about the bus, and we talked about the CDMS, carrier sense multiple access with collision detection algorithm, you saw that you were sending bits and you were listening at the same time to see they were corrupt. That's a kind of error detection. But what we're actually talking about here with regards to this error detection is how the source can communicate something to the destination, so the destination knows when it receives the bits in its packet that they are in fact the right ones. Alright, so most of you will have seen a lot of this, so I'm not going to go into a lot of depth. Also, the complexity goes mad, so I'm going to truncate the discussion a bit later. But the first one is parity check. Parity check is to ensure a sum of bits is odd or even. And this can be over any number, but so for example here in this example we've got 7 bits, which you usually use to encode ASCII characters, and then we have an 8th bit which is going to tell us whether the ones in that set of bits sum to an even or an odd number. Okay, so the point of a parity bit is you can detect 1-bit errors. Now, I'm going to be a bit more precise about that in a moment. If you don't have enough information to correct any errors you've detected, you've only got a single bit and it can't tell you this parity bit here, this is even parity, this is odd parity, they can't tell you which of these bits is actually corrupt. So at this point, if you've got something like parity and you detect an error, all you can do is throw it away. Now, parity is not a very good checksum. But let's just go over quickly how it works. We just look at the bits here and we count up all the bits that are set. In this case, it sums to 0 because there are no bits set. So with even parity, 0 is an even number, so we don't add any bits because we don't need to add any bits to make it even. However, if we want odd parity, what we're saying is all the bits should add up to an odd number. Now, because it adds up to an even number, we have to add one. We have to have a bit set for our odd parity. So now the bits, because it's 7 plus 1, those 7 bits plus this one add up to an odd number of ones. Here, we've got 4 bits. Again, we don't need to set anything for that to add up to an even number, but for odd, we have to introduce a 1 in the parity bit, this is the 8th bit, to make these ones add up to an odd number. And of course, here we've got all the bits set, that sums up to 7 bits. To make that sum up to an even number, we have to add an extra 1 on the parity bit, so that's our 8th bit. So now, with that 1 bit set, we have an even number of ones. Odd, it's already odd, so we just leave our parity bit as 0. So it's a really simple form of check. It's quite limited, you can't correct anything. Oh, that center thing's on again. You know, and it needs a password to do anything to it. Ah, how aggravating. And I've reset the room already. Oh, I'm sorry. University. Grumble, grumble. All right. Now, this is also known as a vertical redundancy check. Because, how do I put this? When you think of the bits as forming a column and summing, you just compute the redundancy check vertically. So you've got a redundant bit here. Sorry, that wasn't a very good explanation. You'll see it more clearly on the longitudinal one next. Parity detects all even errors. Sorry, I got that completely wrong. Parity detects all odd numbers of errors. Whether it's odd or even doesn't matter. It can detect odd errors. So it can detect a single bit error. It can't detect 2 bits of error. It can detect 3 bits of error. It can't detect 4 bits of error. It can detect 5 bits of error. So you see, obviously the point of that, odd or even parity, doesn't matter which, can only detect odd numbers of errors. So it will certainly detect a single bit error, but as soon as you've got 2 flipped bits, you can't really guarantee anything. Okay, now taking that parity check and making it a bit more complex, we can do something like a longitudinal redundancy check. And what we do in this one is we just have n-bit words. So we take our character string, so this is NWEN in binary, and what we do is we take each of those blocks and we lay them in a table like this. So as you can see, we put those individual words inside that block into this tabular array. And then we just do parity of each of these columns. Okay? And we produce at the end parity words. So this is 8 bits instead of 1. But each of these relates to the individual elements. So the least significant bit here on all of these words has the parity done in this bit. The second one, parity in this bit. So you can obviously see you can represent a large number of chunks of words in that. Obviously we can have more than 4 words, and we end up with a bigger parity, but we can have a much bigger piece of data data segment, and we can have quite a lot more checking done. Now, just to give you an idea, the point of longitudinal redundancy checking is that it can detect all burst errors up to the number of bits you've got. So in this case, we've got 8 8-bit words. Sorry. Yeah, you can tell I just did the slide last night. So I should have used a different digit there. So in this case, we're using 8-bit words. We've got an 8-bit LRC, but of course we can have a different number. I should have written M there. So if you want to click the slides M for that first M. In fact, sorry about that error. I'll just correct it now. Magically changed. Okay. If you've got this, what you can do is you can detect all burst errors up to n. That's the number of columns that you do. Okay? And but you can't do anything about bursts that are n plus 1 if there are n minus 1 uninverted bits. Okay, so there's some conditions out there. But the really simple thing is you can detect bursts up to n bits, which is of course the point. Parity can't deal with burst stall. This is a version of parity checking that will allow you to check for bursts. All right. If the block is badly garbled, so you can get a 50% chance of a false positive. So you've got a half chance of passing a corrupted block up as okay if it's heavily garbled. So it's obviously not the be all and end all. Now, then we've got CRC. Now look, CRC you could do several lectures on. Remember, this course is all about getting the idea, having a high-level taste of lots of things. So I'm going to stop talking about CRC in a few slides because I've got the whole principle out. But I do want you to understand, at third year you could do 2 or 3 lectures on this, or in second year ESAT. Anyway, so the point of CRC is it's much more powerful than both the longitude and the vertical schemes we've seen. Rather than the simple addition, it uses binary division. Okay? Now, the nice thing about the scheme, and of course the reason that people designed it, was it can be done in hardware. It just uses shift registers and exclusive ORs. That's the big bonus. You can obviously compute it as well. It's not as hard to compute as it's going to look. All right, so the idea is, and this is really just the high-level view, I'm not going to go into this in great detail, is assume we've got k message bits, and we've got n bits of redundancy. So that's going to be our checksum, those are the message bits. And our entire block is going to be a length of k plus n. That's the bit we're going to transmit. But this is sort of meta information, or some redundant information. What we do is, in CRC, you associate bits with the coefficients of a polynomial. Something about computer scientists, they really love using polynomials of degree k and coefficients of those. So if we've got 1, 0, 1, 1, 0, 1, 1, turns into coefficient of x to the 6, it's a coefficient of 1, coefficient of x to the 5 is 0, so all 0 terms are dropped. We're only looking at the 1 terms in this in this polynomial. We've got a 1 here, so we've got 1 coefficient x to the 4. And so we end up with this formula, which just represents the bits in our message. Now, so yeah, that's what I just said, and so on and so forth. Anyway, the point is, how it's computed is mx is the message polynomial. That's the one we just had on the last slide. That's mx. Okay. P is the generator polynomial. Now this is a standard polynomial that has a standard well-known name. We'll see that on the next page. Then px, as I said, it's fixed for a given CRC scheme. So you've got a whole pile of different possible CRC schemes. That's a known polynomial for the scheme. So as long as the computer at the other end knows which CRC scheme you're using, then it can determine the polynomial. And then what you do to actually use it is create a block polynomial, a new one called fx, which is based on both the message polynomial and the CRC generated polynomial, such that fx is divisible by px. So there's our polynomial division going on, and 3 dots because I could now have 20 more slides. I'm not going to. The point is, high-level view, you're using polynomials, you're using the coefficients of polynomials, and you're using polynomial division to do this. But it can all be done very simply in hardware with shift registers and XOR. And they chose the scheme so they could do that. All right, so what are some properties? CRC 12, this is the generated polynomial for that. CR16, that's the generative polynomial for that, and here's another CR scheme with a very slightly different polynomial here. Okay. Anyway, the point is CRC16 and CRC-CCOTD can detect all single and double bit errors, or odd numbers of bit errors, bursts of length 16 or less, 99.997% of 17-bit error bursts, and 99.998%, yes it's bigger, of 18-bit and longer error bursts. Nothing's perfect, but it's pretty close. So anyway, I wanted to really point that one out to you to sort of show where you can go with the complexity of these checksums. Now, obviously, how much effort do you want to go to make sure your data is okay? A simple parity or something complicated like a CRC? Well, it depends on your media. Some media is really error prone, so you want to use something good like this. Some media, like fiber, has hardly any errors, so simple parity is actually enough. And in fact, down here at the data link layer, fiber often just drops error checking it all entirely because fiber is so accurate. In fact, what fiber usually does is there's no error checking at the data link layer where it normally is. The only error checking that happens is up at one of the much higher layers called the transport layer, which we'll get to later. So it depends how much effort you go, it depends on your media. All right, so this is basically how we do some construction of it using these error detection schemes in the actual art of sending. First, we create the data part of the frame. So there it is, it's blue. We then compute the error detection code over the data, be it parity, be it CRC, or whatever. And as I said, we use parity for good quality media, usually, or no error checking at all, or it's something like CRC for something that's lossy, like wireless. We then chuck that computation into the header along with the addressing information we talked about last time, and then we send it one bit at a time onto the physical layer. When we receive it, okay, we read the frame, and the frame includes both that header information and the data. We read it one bit at a time from the physical layer. And then we compute the error detection. We know what code's used. We set up this communication, so we compute our code over this data. Okay, and then we compare it with the error detection code we received in the header. So just like you saw with digital signatures, we don't try and reverse the error detection code because that's impossible. What we do is we compute our own version of it and then compare it with the one we got set. And it could be your data is fine, but the header got corrupted and the error detection code is in the header as well. It doesn't matter, we still throw it away because we have no way to tell. Anyway, the point is the receiver does its own computation and compares it with the error detection value in the header, in that meta information. And we reject it if they don't match. Oops. So, that's a very quick overview of error detection. Now, I mentioned correction before. The more redundancy we can add, the more computation we do, the more possibility we have of being able to correct small errors. Because, you know, if you've got a single bit error, why retransmit 1,000 bits or 2,000 bits because of a single error? Wouldn't it be better just to fix it? So we can add some form of error correction. And what we do is we add extra bits that allow us to detect a single bit error, for example. If you want to look them up, I'm not going to do them in the class. Hamming codes are one technique. And there's something called a Hamming distance, which shows you how many bits you can detect and how many bits you can correct. And just to give you an idea, you can always correct fewer bits than you can detect. But I think the thing I really want to point out here is this is always a trade-off. It's always a cost to doing this computation. And there's already enough complexity in these network pieces of hardware that you won't want to introduce more. So it becomes a trade-off between the cost of retransmission and the frequency of errors you get and the overhead in the number of bits that you have to transmit and the amount of time you have to spend in computation. And as I've said probably about 5 times by now, favourite hobby horse. The worse the media, the better the error detection and correction that's required. See, the other thing you've got to think about is, when I say cost of retransmission, I'm not just talking about time. If you've got a heavily congested piece of media, if you just retransmit 1,000 or 2,000 bits because of a single error, you've impacted the performance everyone else sharing that piece of media sees, because you've performed some unnecessary traffic. So it really becomes quite a complex trade-off. It's not a simple thing. It's very context dependent. All right. Now, since I've sort of talked about wireless in terms of error detection and correction a little bit, I just want to quickly sort of describe wireless as a shared media, as a bus of sorts. 802.11 has up to 14 channels. This slightly depends on the country, although it's reasonably universal. Each channel is 22 megahertz wide. That's 802.11b. And the point is these 14 channels overlap. Okay, so each of these bubbles is a channel. The ones on dotted lines. This one and these three solid ones are basically considered the non-overlapping channels. So while you can select any of those channels, typically one of these non-overlapping channels is used and they act as a bus. Here's a sort of picture of some of the different standards for 802.11. So this is B. You just saw in the last one. These are the 4 channels typically used. You can use the other channels. If you use one of these other channels, you can possibly interfere with 2 other Wi-Fi devices though. So it's a bit unfriendly and you're likely to get bad performance. This is 802.11g. This is 802.11n. So you see 802.11n has basically got its extra performance by coalescing these channels. So it's coalesced those 2 channels to get much better bandwidth. The channel width is 40 megahertz. I'm not quite sure why it's got that number down there in the picture. All right, so wireless is just the same as any kind of shared media, wired or wireless. All right, so that was kind of an aside. So anyway, look, so far we've seen fully connected topologies, which are really expensive. We've seen buses, which involve things like collisions. And we've seen rings, which can be somewhat inefficient. If we think about it in terms of problems associated with each of these, as I said, there's no real issue with this in terms of performance. It's really just cost to benefit. It doesn't scale, so let's not worry about it. Let's eliminate that. It's not a practical idea. Then, oh hey, what was that? Then we've got buses. Bus is nice in that if it's a physical wire, you've only got one wire to worry about, routing through the building or whatever. There are issues though if you have a network break here, you now have it partitioned into 2 networks, this guy, these 2 guys here, and these 3 guys here. And it can be difficult to locate where that break has happened. You can usually work out the 2 terminals, but in the old days they used to call it walking the line. So they used to have the system administrators walk the line, so they follow the line to find the break. It was usually somebody that would break the computer, which is kind of annoying. And then you've got the token ring, which I'm going to put an X through 2, because if you have a break in this token ring, the token gets stuck and no one can communicate. So it's even worse than a LAN, a bus I should say, because they're all LANs. Here we at least had 2 networks partitioned, but they could still communicate, these guys. Here, the token gets stuck, and the whole thing stops working. So, in a way, it's almost the worst of all worlds. It's inefficient, and it's susceptible to a simple break. Another problem with LANs, as I mentioned, is you can put your Ethernet adapter to promiscuous mode, and look at all the traffic that's going past. Same true on this token ring. Not true up here of our fully connected network. So what we want is instead of the worst of all worlds, we want the best of both worlds. We want sort of security here, because you don't want people snooping on your stuff. You want its resilience to single link failures, like here. This single link failure only affected the two for whom that link connected. Didn't affect anyone else. So what we want is we want that kind of failure mode. So what we want to do, how we solve this, is by adding more hardware. We introduce what's called a star topology. Now this is only for wired systems, okay? Obviously wireless can't do this. Well, it could, but it wouldn't be reasonable.
In wireless, you'd use a router, wireless router. You'd have
you would do it by separate channels, but it's not quite the same. Okay, so because doesn't it? So here what we've got is we've got a star topology, we've got a center node we've introduced. That's a new piece of hardware. So we're solving this by adding more hardware, and each of these devices is connecting to that new piece of hardware in the middle. All right, so the other thing I should probably say about this is how, for example, our labs are all connected and our machines all through the university. Because we've got various machines connecting to a piece of hardware here that's a piece of dedicated networking hardware. Now, the simplest one of these is called a hub. I'm pretty sure everyone's heard of a hub. A hub is a device that looks a lot like a piece of wire. I mean, it's actually a box with lights on it, with flash and everything. But as far as these guys here are concerned, it just looks like a piece of wire that connects them. There's no sort of, I'll talk about this on a later slide, but I want to point out, a hub is what you call it's a dumb device. Now, a hub operates at the physical layer. So when we were drawing that protocol stack, we had the physical layer, and then we had the data link layer up there. Well, a hub operates purely at that physical layer, which is why I said it acts like a piece of wire. These devices here are not aware of its existence. Now, how does a hub work? Well, this computer sends a message, it comes to the hub, and the hub sends it out on all those connected links. So it's just a receive and relay, a receive and forward. This one wants to sends there, and it gets sent out onto all of those. All right, now this is because it's a layer 1 device. We can do better than that. And I'll talk about that in a bit. But let's have a look at what happens when we have a piece of wire fail. Nobody's affected except this guy. So, that's kind of similar to the to the fully connected topology. Only the one directly connected to this piece of wire has suffered with a lack of connection. Likewise, same thing there. Now, hubs are transparent to the nodes. So I said this, but I really want to stress this. Hub acts at the physical layer 1. Okay? It does stuff. It amplifies the signal. It cleans it up. It does stuff. But it doesn't do stuff that appears as to the network. It simply rebroadcasts. And so it's exactly equivalent to a bus. You still get collisions. Okay? Collisions have to be resolved in the same way. So you have to do carrier sense, multiple access with collision detection. Because it's done in exactly the same way. It's just acting like a piece of wire. Hub doesn't care who's connected. You just plug them in. Doesn't care which link it's connected to, because they come in and it sends them out again to everyone. Arriving frames are just relayed on all other links than the one they received on. And because of this, it's just a piece of wire. You don't really have to manage a piece of wire. It's an active piece of wire, but it's not doing any logical network switching or anything. Okay, so putting that hub in solved some of those problems with links failing and stuff. Didn't solve the problem of dealing with collisions. So this is the same slide you've seen before. We're just introducing another line down here at the bottom. So let's use even more hub. Okay, so that was the hub. We're going to replace it with a switch. Now, a hub, remember, was a layer 1 device, a physical layer only. A switch, on the other hand, is a layer 2 device. This operates at the Ethernet layer. This switch understands MAC addresses. This switch understands headers and error checking. Okay, so the switch is now sitting there at level 2, and it has now a presence in the network that these guys could potentially see. They don't, but that's because they don't care rather than they can't. Because if they had to care, then they'd have to think about it. They don't want to think about it. All right, so in general, switches are transparent to the nodes. You can connect to a switch and manage it. But in general, day-to-day data transmission, the hosts don't have to care. Okay? The switch is more complex, it's more expensive than a hub, which of course is a disincentive to use it. And as I said, it operates at the data link layer, at layer 2. Incoming frames are sent only out on the links to which they are addressed. That's interesting. So a hub just broadcasts an incoming message to all outgoing links. Switch does something different. It adds intelligence. It looks at the packet and says, oh, hey, that packet's got a MAC address. Now, I need to send it to the link that's connected to that MAC address. Oh, okay, so that's interesting. How does the switch find out which MAC addresses are attached to which links? And of course, I'm going to talk about that quite a lot. It can also do things like dealing with collisions. So if a link is busy, I just store that data packet until the link is free. So I'm suddenly reducing collisions by adding storage into this switch. So you can see it's quite an active element in our network. And this is the modern way of building wired LANs. And to do this, switches need to know what is connected to each link so they can send out frames on the appropriate link. So this is called store and forwarding. Now, store and forwarding is something we'll come back to a bit later because it's a good idea, but it causes problems. It causes problems in that sometimes packets get duplicated. And we'll talk about that later. It's not the topic today. Now, of course, this additional network complexity means we have to configure it. We have to add management in it. Now, you can imagine doing this manually, where you set up your network, you put everything in the switch table that's connected to every link, job done, and then a machine changes and you have to go in and you have to manage it. The better way to do it is to allow the switch to discover what's connected to it by itself. We don't like to do management. It takes time, it takes resources, and it's, well, boring. So what we want to do is we want to make sure the switch can learn things for itself. So we set up a table in the switch, and the idea of the table in the switch is it should have enough entries for most, if not all, of the nodes in a LAN. It doesn't have to have all of them, but it should be able to have most of them. And when a frame arrives on an incoming link, you look at the table and you say, oh, this is a packet for this MAC address. The device with that MAC address is attached to my interface number 1, so I'll send it out on number 1. All right. So now, how do we go about, actually using that information? How do we go about learning it as well? So the switch has to make a decision on which link to forward that frame, or if to just throw it away. Okay, it may just discard the packet. So imagine you're sitting there as you're a switch, and you receive a piece of data on interface X. Okay, if you don't have anything in your switch table, so you don't know it, you can just act like a hub and broadcast it on all links. And in fact, you do need to do that when you are first bootstrapping, because you don't know anything about the network. So if your table's empty, just broadcast it. Be stupid like a hub. If there is an entry for the address, then we look up the interface that's associated with that MAC address, and we send it out on that MAC address. If the MAC address was the sender's MAC address, so it's sending it to itself, obviously we can just drop it because it already got it. It's sent. So we just filtered it. All right, so let's look at the learning a bit more. As I said, creating a switch table by hand is a pain, so let's do it dynamically. And if you think about it, this makes a lot of sense. If you've got a a mobile device or something, you don't want to be dealing with that all the time. So the table's built dynamically through this self-discovery, and this is how it works. The table's empty, right? At the start, you turn it on, the table's completely empty. Now, a frame arrives on one of the ports, and all it does is record the MAC address from the source. Okay, so the sender's MAC address. Because now I've learned something. As soon as that sender sent me a message with its MAC address in it, I knew that MAC address was connected to that piece of wire. Okay? And we put a timestamp on it. Because networks change, right? At some point, maybe that computer MAC address will no longer be connected to that piece of wire. So we want to make sure that we've kept that information up to date. It can't last forever. Okay, once every node has sent one frame, the switch will know the table will contain every connected node. All it needs is one message to be sent. Now, if you've got a hub that's connected to a switch, then eventually all the MAC addresses attached to that hub that's then attached to that switch will appear in the switch table. And the timestamp, we use aging to purge entries from the table for machines that are no longer in the network. And obviously, the table's a finite space. We just can't keep everything forever. And in fact, we don't want to because it will end up sending fatal messages. So let's have a look at a picture of this. This is a bunch of nodes. These are all machines that will send data. Here's a set of hubs. So I'm just sort of showing you can build these things in a hierarchy. A, B, C, and D are connected to that first hub. That's a done piece of wire. And Q and an unnamed node are connected to this hub. Now, all of these hubs are connected to the switch, and each one of these hubs is connected to one of the interfaces for that switch. All right, so I'm going to number those interfaces. That's interface 1, 2, and 3. And when we build the switch table, we get something that looks like this. Address A, so that's Ethernet address, sorry, that's the MAC address for this host here. A is connected on interface 1, and we saw the message for it at 9:32. This is just a ridiculous time, obviously. You wouldn't use a time that looks like that. B is also connected on interface 1. And we got that pack, the last time we saw a packet from that was a bit more recent. And Q is connected on interface 3 at 7:43 was the last time we saw it. Now look, the point here is that these hosts don't care about these hubs. They may as well just be solid bits of wire. Of course you can't build them like that. And the switch doesn't care about these hubs. It just sees these 4 machines here are connected via interface 1. It doesn't know about this either. Now what happens here is, I've got a circle coming up here showing the fact they share an interface. So if Q wants to send a message to B, Q sends a message up here, it arrives on interface 3, the switch would look it up, find B, finds its interface 1, sends it down to interface 1, and the hub now broadcasts it to all of these. And B says, oh, this is my MAC address, I'll go and pass this data packet up to my application. A says, oh no, this isn't mine, I'll just throw it away. C says, oh no, this isn't mine, I'll throw it away. And D says, oh no, this isn't mine, throw it away. So that's your basic local area network that scales. When we saw the LAN, it didn't scale because the piece of string gets too long, sorry, the wire gets too long. Fully connected topology didn't scale because it was too much hardware. Token ring doesn't scale because it's somewhat inefficient. This here, we have quite a lot of scalability. We've got this hierarchy. All collisions involving this hub okay, resolved within these links. All the collisions involving things connected to this hub are resolved here. This collisions here don't affect here. So we've partitioned the sort of spaces in which collisions can occur. And we've built this hierarchy here, so we've kind of got the best of both worlds. Now, some of the advantages of data link layer switching, with switches, of course, self-learning, is that plug and play. You just plug the wires in, and you go away, and eventually the network or the switch will work out what's what. So that's good. We're eliminating those collisions because if we only use switches, it's stored and forward. If we do use a combination, like in the last thing, it's broken into subnets. We can manage heterogeneous link speeds. Because our switches buffer, switches can handle links operating at different speeds. So if you get something coming on a fast link, a hub would go, oh, I've got to broadcast it at the same speed. Whereas a switch can store it and then broadcast it, so not broadcast it, put it on the correct link at the appropriate speed, which could be faster or slower. And a switch can basically allow you to mix new and legacy equipment as well. You can configure your switches to do some filtering. For example, if you've got a machine that's gone wrong and it's just sending out lots of messages, probably because there's an application that's gone mad, switches can say, I'm getting an awful lot of packets from this guy. This is ridiculous. This is flooding my network. So I'm just going to drop all packets from this link. So you can do sort of limit the impact on your network by filtering out jabbering links. Now, this is an interesting follow-through of switch poisoning. It used to be quite a good attack on switches was done by what you call switch poisoning. And this is kind of related a bit to this idea of jabbering. And basically what would happen is the sender, connected to a switch, would create a whole pile of different MAC addresses as the source and send them through to the switch. It didn't matter where they went. It just meant as long as it got sent to the switch. And the switch would dutifully go and look at it and say, oh, hey, look, here's a MAC address I've not seen before. It's connected to this link, so I'll put it in my table. And eventually, if you do enough of this switch poisoning, the table in the switch will get filled up completely with your fake MAC addresses and your link, pushing out all the other stuff that's actually useful and good and related to the rest of the network. And what happens then is that somebody else trying to send a packet, it arrives at the switch says, oh, you know, my table's full and I don't know you, so I'm going to broadcast. The link that was creating all those fake addresses now receives that packet. So you're now able to sniff. And this technique is called switch poisoning. Okay? It now gets filtered out in modern switches by this sort of algorithm that detects jabbering links that might be filling up the table. But this was, certainly in early switches, this was quite a good way of, taking away the security of separation that you get via switches only sending things down the links to which they are addressed. So, and it was called switch poisoning. It's quite interesting. Look it up if you want. And as I said, damage to only one cable only affects one link. That's true for both hubs and switches. This time, okay. Okay, so layer 2 is a vast improvement on the point-to-point layer 1 sort of stuff we had, or even the hub-connected layer 1. It's got a lot of advantages. It's sufficient for a local area network. But what if we wanted to do something mad and build an internetwork? So an intranetwork is a network within one authority, if you like, one organizational unit. An internetwork is where you connect the networks belonging to different organizations together. It's adding separate networks together. Whereas an intranet is typically one network, but because of ownership. Now look, layer 2 is sufficient for a local area network that can be quite big. But what if we want to go bigger? What if we want to build this internet business? Well, what we need to do is introduce another layer. And we need to take layer 1 and layer 2 and add another layer on it that we'll call intelligently layer 3. And what layer 3 does is it allows us to build an internet. No, I'm serious, I'm not joking. Okay, layer 3 connects networks to networks. So all we've talked about at the moment is a local area network. Layer 3 connects independent networks to other independent networks. And that's what the internet is. Now, so why doesn't layer 2? Why isn't layer 2 sufficient? Why can't we just fill the world with enormous switches? Well, MAC addresses provide a flat addressing space. They're based on the manufacturer. The switches see the MAC addresses for their local nodes. It's flat. It gives no information about where something might be located in the world or in the network. Once networks get bigger, the tables for a switch get bigger and more incomplete, which means more broadcasting, which means more messages, which means we start to get more congestion than we need. You can see where that cascading argument's going. And as I said, just like you saw in the switchboard's name, if you built a big enough network with switches, you'd see a lot of nodes being purged from the tables that didn't frequently communicate because the table space is finite, which would mean, broadcasts. This is inefficient, especially with size. It's okay for small and medium things, but no good for something the internet size. So switches, okay for networks of a few hundred machines, but not thousands or millions. So here's this third layer, and we call it the network layer. If you come from a TCP/IP world, you might think of this as the IP layer. This is the layer that TCP/IP uses to route individual data packets from one place in one part of the world to another place in another part of the world. So this is the big cheat. Okay, so the first thing I want to talk about is the new piece of hardware we have to introduce at layer 3. We've got hubs at layer 1, we've got switches at layer 2, we need some hardware at layer 3 too. Let's call it a router. If you were good Kiwi, you'd call it a router. I can't do that. So the point is that this router, he says being extremely American, sits here and enables packets to be routed from one network to another, hence inter-networks, hence the internet. All right. Now, let's talk a bit about, in my 2 minutes remaining, obviously I'll have to come back to some of this material. The world exists in a funny sort of... The networking world exists in a funny sort of set of layers. If you're talking about the 7-layer OSI model for networking, there are 7 layers. Physical layer, data link layer, network layer, transport layer, and so on, session layer, and so on and so forth. If you're talking about the internet world, you're talking about 5 layers. You've got a network access layer, which has elements of physics, which encapsulates, doesn't actually do this, it encapsulates physical layer, data link layer, and part of this idea of a network or internet layer, you see they don't quite line up. So I want you all to realize that there is always this distinction here between OSI and the TCP/IP layer structures. And the main reason for this is the OSI 7-layer model was built to describe all the layers from basic pieces of wire through to a global network, whereas TCP/IP was built to connect networks. It didn't care what you did within your network. It didn't care. It was only there to build an internet. So it sort of squidged all of these bottom sort of layer functionalities that we've just spent the last lecture talking about into one whole big chunk called the network access layer. And basically what TCP/IP was saying was, this is somebody else's problem, not my problem. I'm only interested in connecting network to network. which is cool. And as long as you understand that's the reason, then the difference between a 7-layer OSI model and a 5-layer TCP/IP model becomes a bit clearer. Anyway, I think from my numbers I've just talked about, you can see we're going to talk about another 4 layers up here and another 3 layers up here. Now, just to finish the slide, what we need at layer 3 to handle a global internetwork is more intelligence even than we saw in a switch. And it has to deal, and this is the big point, a switch generally knows every node in the network that it's connected to. We can't do that on a global scale. So we've got to build a system that can deal with vast amounts of missing information. Very incomplete. And so the basic way of doing this is to build a hierarchical addressing structure so that localities know more, and as we go up the hierarchy we know less, but we generalize more. So we can say, oh, I don't know anything about these hosts, but it's probably from that region, so I'll send it down there and let that region deal with it. So it's all about this idea of delegation and hierarchy. And we'll talk about it obviously next week. If you want an extension till Monday midnight for Project 2, please email me. I'm not sure what my threshold is, but there is a threshold. If you object to people in your class getting an extension, I suppose you're also welcome to email me. All right. Right, thank you, and see you next week.